Stanford University.
We are very, very lucky today to have two real experts on this topic. The first is Matthew Wald from the New York Times. Matthew has been writing about energy topics for 30 years. He's been in the paper's Washington Bureau since 1995 and is currently assigned to write about the environment and energy. He's been particularly interested in civilian nuclear power since the 3 Mile accident and has toured more than 24 nuclear power reactors and researchers' reactors, as well as the Yucca Mountain site, which was, of course, as many of you know, was recently the candidate for the U.S. waste disposal for civilian radioactive wastes. So that will be our first speaker, but now I would also like to introduce our second speaker, our own Burton Richter, who is the Paul Pigot Professor in Physical Sciences at Stanford, and of course the Director of Emeritus of the Stanford Linear Accelerator. We all know him as one of our real energy experts, and he just wrote a fantastic book called Beyond Smoke and Mirrors about all of these topics, and he's deeply knowledgeable about nuclear power and has thought deeply about its future and including its important role in dealing with the climate change issue. So with that, I would like to get on with things. So the way we're going to do this is we're going to break it into two parts. First, we'll talk about just the facts, what happened in Japan. And first, Matthew will give some perspectives and information about what happened, and then Burton Richter will follow up with that. We'll then switch to the second topic of what does it mean for the future of nuclear power. And Bert will first talk about some of the international issues around that, and then we'll bring it back home to the United States where Matthew will address those issues. So with that, please join me in welcoming both of our speakers today for this very important event. So thank you.
Thank you, and I hope you can hear me, or you'll trip and wave your arms if you can. I'm going to start with a brief shell. We keep hearing about melting nuclear fuel. Well, for years the industry had liked to give away these little card reactors that simulated nuclear fuel pellet. In real life it would be uranium dioxide ceramic, and on the back it says that, rather on the front, is that this is the energy equivalent of 3 barrels of oil, a ton of coal, or 17,000 cubic feet of natural gas. And the reactor, it sits in a long, thin metal tube of a zirconium alloy. The tube gathered into bubbles and will sit immersed in water or steam. Nothing. Item 2 is the instant nuclear plant. Arriva wants to build a chain of these in the United States, in Olkiluoto, Finland, and it's like a kid's pop-up. You open it up and the real thing costs probably $10 billion and takes many years to build, but this one's quicker. I've also brought along, we hear that the Japanese do recycling, the French do it too. I mean, well, they chop it up, they retrieve the unused uranium, although they actually use it. They also retrieve the plutonium that was created in reactor operations, and they take the remaining in a very strong form of glass, borosilicate glass. This particular came from a military facility in South Carolina, the defense processing facility, which is leftover bomb wastes, quite similar to civilian wastes, and the cesium and the other isotopes, and then you wait to put them in, and then you wait some more, and then you wait some more. And I got one other artifact to show you, which is I bought these things 20 years ago. It's a it counts gamma radiation. You put a button, and it lights up, and it tells you how many millirentgen you've got, and it chirps like a little smoke alarm. A couple of weeks ago, I was going back over the instructions for these things because we shipped, and it said that the device was about the size of a beeper. And I realized most people didn't remember what a beeper was like, but if we go another 20 years before we use it, what am I going to compare this to? A pack of cigarettes? What physical object can I put writing that will still be able to recognize 10 years from now, 20 years from now. Anyway, if we can go to the first slide, I'm going to talk through how Fukushima is supposed to work, what's happening to it now, and what happens next. And I can't see from the camera is now. Do we have the first slide on the screen? Here we go. Okay, so this is a short video that was taken by a plant employee on his cell phone, and it was the wave coming in. We've survived the earthquake, and here comes the wave. And if we can go ahead and play that, it's very short. Well, that's short. The height of this wave has varied depending on when you heard about it, but here we go. Tokyo Electric Power got out there. You see that spurt? That's the wave hitting the front of the building and spurting up into the air. And they looked at where the waterworks were. And this was not designed for that. No plant was designed for that. Maybe it should have been designed for that, but it wasn't. Okay, if we can go to the first PowerPoint slide, which is of Fukushima in bad times. Maybe we got to play out this whole video. The guys from Tepco all wear these ugly blue lab coats. I think they'd be more beautiful if they street. Well, while we wait to get that slide up, let me tell you what we're going to be looking at. Fukushima Daiichi, which Fukushima 1, there's a second plant a few kilometers away called Fukushima Daiichi, which is Fukushima 2. Fukushima Daiichi is a complex of 6 reactors of sorted. The Japanese like boiling water reactors relative to the other major technology that uses ordinary water called pressurized water reactors. The light water reactors are very good for you can vary their output up and down over the course of the day, which is important if you're going to put 6 in one location, half dozen a few miles away, and if you're going to run your whole system on nuclear power. In this country, that seldom gets to be an issue because only 20% of our electricity is from nuclear power. But if the thing can't run out full time, it doesn't make it. It doesn't. The most reactors one spot is 3. That's in one Connecticut and another in Arizona. There's a place in Georgia where we have 2, trying to build 2 more. That would give a. Here we go. So this is Fukushima Daiichi. The square boxes towards the top are the reactor buildings. Those are the things we saw blow up on TV. The lower, broader buildings are the turbine buildings, and we'll look at some schematics in a minute. That's where the steam is converted to electricity. And in the very foreground, you see tanks that probably stored cooling water, and I doubt those survived. We're looking from the ocean land here. And go ahead to the next slide, please. That's before and after. You see one of the secondary containment systems active, going up. You look at turbine hall on the left, and you see holes in the roof, and there is debris all over the place. This place was needed everything in its place, and it has been smashed. Nuclear reactors are actually in a hurricane, a cyclone, other kinds of events because they're class 1 buildings. They built stuff. But this place has been smashed. Go ahead to the next slide. We're going to walk through a series of diagrams here that get increased. Okay. Well, this is called a boiling water reactor. It uses ordinary water as but coolant is really the wrong word. It's really fluid. The reactor produces heat, steam. It's called boiling water because you boil the water directly in the core. You take it to a turbine, it's a little propeller, that converts some of the energy of the steam into free power, which turns the generator. The generator makes electricity. The steam actually very valuable water. It's extremely, you don't want to lose that. That has to be converted back into a liquid in order to be heated. You lose about 2/3 of the energy value in converting it back to, and you do it by running it over some pipes. On the inside of the pipes, you have cold seawater, and then you pump it back in for another pass. The reactor has fuels, and there are control rods that have to come up from the bottom in this design to shut off the reaction when you need to do that. When the reactor shuts down, there are big valves that close over the steam loop, so they keep the reactor bottled up in the containment building. In normal operation, you're letting some of that radiation out, that radioactive material, because the loop has some radioactivity in it. The coolant water is forming actually different functions. It also acts as a moderator, which means it slows down the neutrons as they're emitted in the chain reaction, and it's optimum speed for putting more neutrons, more uranium nuclei. And the reason that some people like boiling water reactors is liquid water is a very good moderator. Steam is not a very good moderator. Change the efficiency here. You want to change the population, and do that to the proportion of steam bubbles in the core. And you can do the design. Go to the next slide, please. Here is a slightly more complicated view of the same. Here what we have is that upside down light bulb is the containment. That's the thing we think is intact in units 1 and 3 and damaged in unit 2. It's bottled up tight, as you can there. It is a lot smaller containment and thinner containment than a pressurized water reactor, but it's believed to be adequate because it's got a couple of useful. One of them is at the bottom, you see that circuit part, we're looking at it in cross-section. It's called the web torus, and it's half full of water. It's got about 1 million gallons of water in it. It up with surplus steam when you took the well. That worked well at Fukushima until they had so much surplus steam that they took the wet well. There are two methods. The primary containment cooling reactor. One is just discussed in the simpler. Pump the steam off to here you can see the main steam line goes to the turbine generators, back through the condenser, and then is pumped back in for another pass. Excuse me. The other method is when you shut down, you're still producing heat. At the moment of shutdown, you're producing about 6% as much heat as when you were running, because you've got lots and lots of very short, several seconds, several minutes, several hours, and as the atoms seek stability, they're throwing off a gamma ray or an alpha or beta particle, they give off heat. It decreases pretty quickly, but you have a very substantial heat load at the beginning, and the down cooling is you pump water out into the condenser through a loop not quite shown here, and then back in again. They lost the ability to do that when they lost the diesel generators. When the tsunami came in an hour after the shutdown, the control rods were in place, there was no nuclear, they lost the ability to remove, and that's where their troubles really began. Go ahead to the next slide, please. So here is a view, a more realistic. We see the torus at the bottom. That red capsule up and down is the reactor vessel. It's actually fairly small, and it's in here. The diagonal pipes lead down from the primary containment, from the dry well into the wet well, and that's where this would be. You see there's an itsy-bitsy of a man in the torus at the bottom right. That's just shown for scale. Actually, nobody in his right would be in there. In this picture. We also see in this picture the spent fuel pool. If you see the head of the reactor, you see to the right of that is the spent fuel pool, and the way you refuel this thing is over the head of the reactor, we've got a lid on the primary containment, and over that, we've got some concrete blocks. You use the crane, shown here parked on the right, that red thing. It rolls over, picks up the blocks, removes the top of the containment, removes the vessel head. Now, all that has to be done underwater because the radiation field is so high. So during refueling, you flood the area over those blocks. The crane then will pluck out individual fuel assemblies and move them over to the spent fuel pool. You may have heard about this design that one of the problems is the spent fuel pool is up in the air. This has some advantages. You're able to move the stuff quickly. The amount of time you spend moving each individual assembly is quite short. That keeps your outage short. The disadvantage is in case of earthquake or in case of Mohammed Atta in a 757 or various other problems, the theory is that that pool is a little more vulnerable. Anyway, here, this is a good image of both the primary containment and the secondary containment. We're, of course, looking at a cutaway view here. The secondary containment up on the top, that's the thing that blew up when they had hydrogen that they were trying to vent from the primary containment to the exterior, but ended up in the secondary containment again. Before you can clean this up, before you can defuel that reactor, you're going to have to rebuild that secondary containment. Let's go on to the next slide, please. These are our fuel assemblies. So I had showed you previously my show and tell, our little pellet here. The pellets sit in those rods. The rods are bundled together, and the whole thing is wrapped in a zirconium sheath. Both the rod and that bigger wrapper. Zirconium is not chosen for its strength. It's not chosen because it's chemically inert. It ain't. It's chosen because it's transparent to neutrons, and the whole purpose is to multiply the population until you have a lot of neutrons that will carry on the chain reaction. This is what, by the way, this is what sits in spent fuel pools. Go on to the next slide, please. This sequence, I think this was circulated by the Nuclear Energy Institute, the industry's main trade association here. Top left, core uncovered. Usually, you have the whole core either bathed in water or some mixture of water and steam, in which it's mostly water. The core uncovers, the zirconium clad starts to melt, those little pellets start falling out. So we go from core uncovered to, in not very long, fuel overheating, and then we get the fuel elements slumping, some of the pellets falling to the bottom, and we get this molten mass in the middle. And then looking across the bottom, you see the first slide, which we hope is still our case. We get the core damage but retained in the vessel. The theory is if you go long enough, some of it's going to melt through into the lower reactor pressure vessel, and then possibly even get out of the containment. One of the problems here is the zirconium clad and those zirconium channels react with steam, and they give off hydrogen. They go through a sort of rust-type reaction. They dissolve into a powder. They give off hydrogen. If you have oxygen handy, you will get an explosion. Go on to the next slide, please. And as I said, I'm showing you a variety of schematics of differing complexity. This one, the point I wanted to make is you introduce cooling water on the outside. It goes down to the bottom of the vessel. It flows up through the core, and then you get the steam out the top. The problem with this design is once you mess with the geometry of the core, once you've started melting that like it's a bunch of little birthday candles that are parked too close together and melting each other, once you get to that situation, water's not going to flow very well. You have hot spots, you have molten areas. Once you start dumping some of the core into the bottom of the vessel, that's going to be a problem too, to keep it cool. Once you start putting in salt water, because that's all you have handy, you have an additional problem, which is you're not removing heat from the salt water, you're actually boiling away the water to keep it cool. It's called feed and bleed. It's like you had a pot of boiling eggs on the stove, and for some reason you couldn't turn the stove off, so you kept putting in more water. All of that heat is going up as steam. You're concentrating the salt. Well, the salt is going to start to mess things up. The salt is going to start to block things up. Now, we have an additional problem here, which is they managed to overpressurize the whole system in the first few hours. You see the things labeled jet pump on either side. There are recirculation pumps that are actually located a little lower down towards the bottom than this schematic indicates. and they blew the seals on those, which means you've got reactor water leaking out of the vessel into the primary containment, and possibly you've got bits of fuel that have been atomized or broken up into suspension. So we're starting to spread our fission products, all the things that the uranium was broken up into, the highly radioactive stuff, the cesium, the strontium, the iodine, etc. We're starting to spread that over the whole plant. Go on to the next slide, please. This is yet another view. I just want to give you the feeling that it's complicated in there. It is crowded. There are defined flow paths, and those flow paths probably don't exist anymore. This is a good view of the ability of at the bottom we've got the control rod drive motors. The control rods actually live in the vessel, but there's a penetration at the bottom of the vessel for each one of those shafts that's going to push the control rod up between the assemblies. Those are potential leakage points. So there are many other potential leakage points. We've got the core grid, which is no longer a grid. Now, one of the theories was you get the fuel slumped together, and then you get a renewed reaction, a renewed chain reaction. You have no way to stop it because you don't have geometry anymore. You can't insert the control rods. It's a matter of conjecture by engineers whether that's actually possible. That's where the idea of the China syndrome comes from. You get the core to become a molten mass at the bottom, it burns its way through, and obviously the term China syndrome was invented by Americans. If it melts all the way through to the center of the earth and comes out the other side from Japan, it's not going to China. I have a reporter who lives, I have an editor who lives in Baltimore who's very concerned about this. So I told her I looked it up, and actually it comes out in Baltimore. In reality, it comes out somewhere in Brazil. But I don't think we're going to get a China syndrome. I think you may have, there's scattered evidence for inadvertent criticalities, little pockets where you can get a renewed chain reaction. That produces lots of heat, steam, energy. It blows the mass apart. You lose your critical mass. It might be reestablished. We may be having that, we may not. It may take years to figure that out until you can open this up and see what went on inside. And let's go on to the last slide. This is yet another view. What we have here is the primary containment. They flooded the dry well, that upside-down light bulb that's usually kept dry. They pumped seawater into it, first water and then seawater, in a desperate effort to cool the core, which is that red box in the middle, and they figured they could draw heat off from the exterior. What this shows is one potential configuration, although it's not clear we have this now, and in this configuration, we've got the fuel slumping down to the bottom of the vessel, burning through, ending up at the bottom of the dry well. Down there is some concrete, and this could turn into a problem because if you heat concrete enough, it'll give off hydrogen and carbon monoxide, and those can combine explosively. We're also looking here at the torus, which is much too full. They've been venting out of the torus. The idea was to vent to the exterior. There are some differences between Japanese plants and American plants, but I hear contradictory information about them. This was not originally designed with a vent. They added the vent later because they figured they might get into this kind of accident. They didn't want to overpressurize. American plants have hardened vents. They look like sewer pipes, and that will carry the explosive hydrogen out to the exterior. The theory is that the Fukushima plant had vents that looked like ductwork in your house with a forced air heating system. And the ductwork ruptured. You got the secondary containment filled with hydrogen. Hydrogen will explode at a very broad range of concentrations with air. Something set it off, and poof, they blew away the external containment, leaving the spent fuel pool sitting out in the open. Actually, I think we do have a couple more slides here. One of them is going to show the spent fuel pool in the, I'm sorry, skip this one, go on to the next one. So here we have the spent fuel pool on the top right, and if it was empty, the U.S. Nuclear Regulatory Commission seems to think it was empty at one point. It's generating heat, it boiled off, they didn't get any more water in there in time. The cladding on those rods also generated hydrogen, and that's how you got a hydrogen explosion in Unit 4, where there was no fuel in the actual vessel. Now, I'll give you a quick update on what's going on today, which is A few hours ago, the Japanese announced they're going to plan evacuations in a more leisurely fashion at greater distances. This is kind of disturbing. It's not because of acute exposures, it's because they've dumped so much long-lived radioactive material, probably cesium, in the area that it's not safe to occupy it for long periods. So you'd be fine there for a day or a week, but if you're going to spend year after year there, your dose will be too high. We're now talking about either a massive cleanup challenge or land abandonment, a la Chernobyl, at least in some hotspots. The other thing is that the Japanese are preparing to upgrade their assessment of this accident on the 7-point international scale. At the moment, it's at 5, which is where 3 Mile Island was, and they're about to reclassify it as 7, which is the most serious and where Chernobyl was. One of the differences is most of this radiation was spread locally or spread over the ocean. Chernobyl spread radioactive materials over enormous land areas and areas that were not very well prepared for it. So it's more reactors than Chernobyl was. It's happening in a place where they're somewhat better set up to cope with it, although it's a mess to try to cope with a meltdown or 3 meltdowns in the spent fuel pool right after a tsunami. And that's about all I know. And I'll turn it over to Bert.
Thank you, Matt. I've never done a duet like this, and we'll see how it goes. I want to do a little bit more about Fukushima, and then I'm going to switch gears and go talk about the future of nuclear. This is Japan. Japan has a lot of nuclear power. They've got 55 reactors. They got more than 20% of their electricity, and they get a lot of their total energy consumption from nuclear. Japan likes nuclear because Japan has no real sources of fossil fuel, and they're all concerned about their national security. So we had the earthquake. One of the things that people don't understand about this earthquake is that, in fact, it was within the design of the plant. The design basis for things like this is not earthquake magnitude, it's acceleration. The ground moves, it shakes. Does the thing fall over? This thing was within the design. A magnitude 9 simply meant the shaking went on for longer. So it's not that there was any screw up here in the design of the plant as far as the earthquake. The problem was the tsunami. The tsunami, their seawall was only 20 or so feet high. The wave was 45 feet high. Why that was done, I don't know. And there you got all the trouble. As Matt said, you've got to keep this fuel cool even after you stop the reactor. Right afterwards, 7%. A year afterwards, 0.1%. And that fuel has got to be kept in water for 3 to 4 years before you can take it out and not worry about it melting itself. This is a look at the radiation release that goes with all of the explosions. Every time you saw a hydrogen explosion, you see a big spike in it. And the spikes go way up above what is the normal background radiation. The average background in the US is about 0.3 microsieverts per hour. This is microsieverts per hour, so way down. Let's see if this thing works. It does. Way down here at the bottom is the normal background. You can tell what's failing because of the signals you get from the radioactive material. When you start to see things that only are produced as fission products, you know something has broken. The first thing that goes bad is the cladding, and then you get the gaseous products released, and those with low vapor pressure, and then the fuel itself begins to crumble, and now you get different materials out, and you can keep pretty good track of it. This is a look at what the radiation levels are outside the plant. Now remember, I said that in the US, the average is about 0.3 microsieverts per hour. This region of Japan is lower than that. There's very little rock here. It's all sort of dirt and so forth. And their level is about 0.1. This is almost at background, and you can see these things decaying further. As of now, the radiation levels, as Matt said, are low. But it's not the radiation levels, it's the problem of living with things for a long time and ingesting fuel, radioactive material. The danger from another explosion is low at the moment, and the amount of additional radioactive material that's likely to be deposited off-site is small. Now, for the students and for the people interested, I've included a couple of slides of information sources and references for those of you who want to read more about this. And now I want to switch gears to the future, and I want to start off with nuclear accidents. Now, Matt has shown how young he is because he doesn't know where the term the China syndrome came from. It's actually the title of a movie with Jane Fonda, and the movie came out within 2 weeks of 3 Mile Island, and the scenario was just as Matt described it. The fuel melted, the fission went on in this lump, and it slowly melted its way down through. I don't remember how Jane Fonda saved the world, but she and her hero did, and if she remembered, maybe they should send her over to Japan right now. So we had 2 very big accidents before. 3 Mile Island, partial core meltdown, containment buildings, little radiation off-site. And if you want to read more details, that's the URL of the Nuclear Regulatory Commission's review. And in fact, one of the people who was on that review, Bill Mady, is sitting over there in the corner. So if you ask nasty questions about that, I'm going to refer it over to him. Chernobyl was the world's worst. Chernobyl was both a power reactor and a plutonium producer. It was a reactor not used for civilian purposes outside the Soviet bloc because it could become unstable. The operators moved it into an unstable region, disabled all the safety systems. It ran away, and you had a steam explosion, not a nuclear explosion. Just the cooling water just flashed to steam, blew the lid off the reactor, blew the lid off the building. Fire started in the carbon moderator, and there we were with the world's worst accident. Wikipedia's article on Chernobyl is quite good. So what happened after 3 Mile Island? That's relevant because things are going to happen after Fukushima too. There were major changes in safety regulations, many modifications made to plants to handle the loss of coolant, and something new set up called INPO, the Institute of Nuclear Power Operations, set up by the industry to exchange information, to work with the Nuclear Regulatory Commission, set better operating standards, et cetera. The setting up of this made huge amounts of money for the nuclear reactor operators, although they opposed it at the beginning, because one of the results of creating INPO is that the uptime of the reactors went from around 60% to more than 90%. So you got 50% more electricity from the same reactor that you'd already built. It was a good deal, and Chernobyl was a different case entirely. That's the remains of the reactor. That's a picture of it before it was entombed in concrete using robot cranes and all sorts of things. There are several reactors on the site. This is the only one that went, blew up, and it now is buried in concrete. You can't see this. The whole thing is covered, and they're going to have to go do something about that. So now after Chernobyl, safety reviews and improvements in the RMBK, the Chernobyl-type reactor, were undertaken by Russia and the IAEA, Many of them were shut down, others modified to improve safety systems, and in fact, a lot of the money for that came from the European Union and the United States to fund cleanup in the states of the Soviet, well, in the Soviet bloc. Russia handled its own. INPO went international, and now we have the World Association of Nuclear Operators, WANO. I don't know whether anybody calls it that, but that's it. Now we had one more thing, which wasn't a nuclear thing, but it was 9/11. That caused extensive reviews for the adequacy of containments if they're hit by aircraft, security of the plants from terrorist attacks, and substantial improvements in security. And most of that is classified because they don't want the terrorists to know what the new security things are. Some auxiliary systems are strengthened, and now any new thing has to have security from an airplane crash. Now, let's look at the world. If you look at the world and look at electricity generation, in the world, coal is the big thing, gas is next, then there's electricity, well, no, yeah. Then there's nuclear is the next big thing, 20% in the US, 16% worldwide, and then after a big hydro, much lower values for the renewables. Nuclear reactors are all around the world. There are about 400 of them now. Of that 400, roughly 25% are the boiling water reactors like that at Fukushima. At 2009, when I got this, there were 435 in use, 28 under construction, 200 planned. Now there are more operating, 58 under construction, and still more planned. Nuclear had become a big thing. And nuclear became a big thing for different reasons depending on where in the world you were. If you looked in Asia, what you saw was a desire for energy. Desire for energy and national security. And so they wanted to go nuclear to get more electricity without having to import more stuff. China, by the way, has to import coal now. Even though it has coal supplies and a lot of coal-fired power plants, it imports it. So China had a good reason to do it. Japan and Korea were continuing their increase. A lot of countries new to nuclear were talking about them, and in fact, some of these countries have already put in purchase orders for new reactors. So in the US, nuclear power plants are prepared for extreme events. The criteria for nuclear power plants are set by the Nuclear Regulatory Commission, and the Nuclear Regulatory Commission was split off from the then Atomic Energy Commission, now Department of Energy, many years ago when people became worried about the problems of the regulators and the referees, the regulators and the promoters coming from the same agency. This is the problem in the oil problem in the Gulf. The people who regulated the drillers were from the same agency that promoted the drilling. Bad idea. India, last week, changed. And India set its regulatory commission free. It set it up as an independent organization. In Japan, the regulators are not independent of the agency promoting nuclear, and there has been no move yet to make them so, but I'll bet you that pretty soon there's going to be such a move. So you should think about things in a little bit different way. Old and new reactors going to have to review safety requirements, review old ones and see what needs upgrading, review the designs for new ones and see whether you have to do more. You're going to have to look at multiple problems again. They are looked at now. So think about multiple problems. You think about earthquakes, tsunamis, hurricanes, tornadoes, floods, forest fires. All of that's going to be reviewed to see whether the requirements will handle any conceivable multiple disaster scenario. And another thing that's going to get reviewed is how long the reactors have to go on their own. All the reactors have emergency generators. All our reactors can survive entirely on their own with nothing coming from outside. But I don't know the number for how many days they have to survive that. Fukushima lost all outside electricity, lost all outside cool water, pure water, for over 2 weeks. And the only reason it has fresh water now is our Navy came in with 3 huge barges full of fresh water, which is where it all comes from. Matt mentioned there's a difference between the boiling water and the pressurized water. And the difference is what's inside the containment. This little thing down here, come on, this little thing down here is the reactor. All these other things are steam generators, pumps, all the rest of it, and this is the containment. In this reactor, new design, generation 3+ called, the reactor vessel is 15 feet in diameter. The containment building is 100 feet in diameter. There's a lot more stuff in there. So all of that is going to get reviewed. Now, one of the things you should also know is that there's general agreement in the world that the U.S. Nuclear Regulatory Commission is the gold standard of licensing and regulating reactors. Even the French agree that our system is much tighter. And I say even the French because the French get 80% of their electricity from nuclear. And the French also have one of the companies that is one of the leading manufacturers of nuclear reactors. Everybody is going to toughen things up. I think we need to keep this thing in perspective. And there are 2 perspectives you should think about here. One perspective is a tsunami. There are already 14,000 dead and another 14,000 missing. There'll be 28,000 people killed in this. The only people killed so far in the reactor accidents are 2 people inside the building, and they think that things fell on them. They don't know yet what they died of. But this is a look at natural radioactivity in the U.S. Some of us old guys still use millirems instead of sieverts, but a sievert is 100 rem. So if I say millirem here, that's 2.4 millisieverts. This is a year's dose. So you get 240 from natural. 40 of those, 240, come from radioactive potassium in your own bones. How much you get depends on how big you are. A 160-pound man gets 40 MR. Medical gets another 60 on the average. So typically, it's 300 averaged in the Americas. And a nuclear plant emits practically nothing. And nuclear plants and coal plants operating together are about the same. An analysis has been done. This was done in Germany. You can see the reference down here in the corner. They looked at all of the sources. This is cradle-to-grave health risk. Cradle-to-grave means from mining to transport to making ore to doing whatever you have to do, to using the stuff, to disposing of spent fuel or ashes from a coal-fired power plant or what have you. And if you look at this, the conditions required here are what the European Union requires for emission controls. There's a new one that's been done by the U.S., for the U.S., which doesn't handle as many things. It only looks at the fossil fuels versus nuclear. But the general conclusion is the same. If you look at years of life lost, you find nuclear sitting over here, and the only thing better than nuclear is wind. Photovoltaic, more years of life loss per unit of energy. And then you can find all sorts of health problems down here. The moral to the story is that the issue is what is the hazard? Now, we got a funny thing with people. We're all people. We get scared of things we don't understand, and we're also scared of things which do a lot in a very short time. We all drive cars. 30,000 people every year get killed in automobile accidents, but that doesn't make us ban automobiles because we all feel we're in control. Nobody feels they're in control with a nuclear power plant, and they don't realize they're not in control either with a coal-fired power plant or with the manufacturing of photovoltaics or whatever one you want to pick. So there is going to be some review, and there is going to be a public perception problem. Interestingly, there's a new poll out, and the new poll asks the question of should we do more nuclear? And the people, fraction supporting it went down. Then the poll asks the second question, should we shut down our present nuclear plants? The answer did not change from before Fukushima. So people are perfectly happy to keep them going. There is a concern about it. So let me give a summary and then get Matt to bat cleanup on this. Fukushima was and still is a serious accident. There's going to be a rethinking of reactor safety and the setting of what's called design basis criteria. How big the earthquake, how big the tsunami wall, et cetera. Regulators around the world are going to be given more power, and I already mentioned India is the first example. The actual impact of Fukushima compared to other conventional sources is going to be small, but radiation is feared, and it's too soon to see the impact on public perceptions. Personally, I think the attitude around the world, the change is going to be quite small, and I really don't know what's going to happen in the U.S. With that, Matt, back to you.
Right. Well, thank you for telling me I'm too young. Best news I've had all day. United States, it's not public. I agree with everything you said. Public sentiment or even public acceptance that's required for construction of new nuclear plants. The polls are mostly national. You don't need national to build a reactor with the whole community in a hospital state. And there are lots of places that would be delighted to have a company announce, we're going to spend $5 or $6 or $10 billion on construction in your neighborhood. We're going to provide a continued tax source for the next few years, etc. I was up in Maine where they were tearing down the old Maine and a plant that had actual safety problems. The school across the bay, what industrial that site would be put to next, because the news was quiet and they didn't know what was going to happen. You could put in a noisy factory that would make life very difficult at school. In the United States, what plants is not public sentiment, is the profit motive. And the problem for nuclear right now turns to be nuclear waste, not to be Fukushima, not to be other generalized fears. It's not to be natural gas at $3.50 a million BTU. A nuclear plant today is probably the value of the natural gas it saves, plus the value of the carbon it saves. Now, because we're sitting on more natural gas than we thought we were, technology has improved the recovery method. The fracking, which produces lots of natural gas, does in fact have environmental downsides, but it's not clear how much of a hindrance that's going to be. So we've got no price on carbon. We've got no prospect of a price on carbon. We don't need nuclear power for energy independence. The companies that would do it because they think they can make money at it. At this price, nobody can make money building a new reactor. So we had the 2005 Energy Act set aside $18.5 billion in loan guarantees. These aren't loans, these are just the government. It's like I would go in and co-sign a car note for my kid, an $18.5 billion car note. And there were 4 leading candidates. Of the 4, the one in Georgia, they've actually broken ground. That's the Southern company, the Vogel site. That's the one that may end up with 4 reactors. There's another across the Savannah River in South Carolina where they've broken ground. They don't yet have permission to build, but they're building these enormous holes in the ground with good foundations. The 2 others were my pop-up nuclear plant here, which is the Ariba design. There's a company that wanted to build one of these in Calvert County, Maryland, about 50 miles south of the District of Columbia. The French, Ariba itself and Électricité de France were going to be partners, but the local company, Constellation Energy, which used to be Baltimore Gas and Electric, got cold feet. It looked at the price of electricity plunge in the eastern electrical market because we're in a recession, because natural gas is so cheap, and it said, we can't make money out of this. The French said, well, we'll just find another partner, but they haven't succeeded in doing that. So there's a loan guarantee that they go begging. The other one is in Texas, the South Texas project, where the company that wants to build was told by the U.S. government it couldn't get a loan guarantee unless it got contracts to pre-sell some of the electricity. The likely buyers, munis, co-ops, etc., were not interested in buying because they didn't think that the project was ever going to happen. The company that wants to build, it's a New Jersey company called NRG, did line up some potential investors. One of them was Tepco itself. Tepco was going to take a 10% stake. I don't think Tepco is in a position to do that anymore. That reactor was a shaky prospect before the accident, and it is a shakier prospect now. So at the moment in the United States, we've got 104 reactors. The TVA is trying to finish off 105th that had started in the early 70s and then let sit in mothballs for years. We've got 3 that are likely to be approved and built. They're in a part of the country where the risk of building the wrong thing will still lie with customers. It's not like California or the Mid-Atlantic states where we have a market system. It's a traditionally regulated system where the customer takes the risk, gets the benefit. I don't foresee a lot of other reactors getting built here, but on the other hand, I didn't foresee that before Fukushima. The Chinese have a temporary hold on building, but they'll go back to building, and so will the Indians, because they don't have the coal, as Bert said, and they have a very rapidly growing demand. We do not have rapidly growing demand in this country. In fact, for the last 2 years, it's actually shrunk. And I have no
Ms.
idea.
Benson runs it.
Oh, can you hear us?
You will in a second. I've got to talk.
Oh, okay. All right.
I'm sorry, I know that Lee is speaking, but I don't hear anything.
Oh, can you hear me? Or no?
1 minute, and then you'll hear.
So why don't you start off with a question for me, and then we can do it.
Okay. Well, we will. While we're waiting for that to sort out. So when he comes back, we would like him to have the opportunity to wrap up. But then we'll move on to questions. And anyway, how are we doing with the audio up there?
Okay, I hear you now. Go ahead.
Okay. So did you have some more remarks that you wanted to make, or are you?
No.
Okay, great.
Thank you.
Okay, so we will now. Okay, now we'll move on to questions, and so you can ask questions of either speaker, and and typically we like to ask the students first, so don't be shy, and Jaya and Noel have got the microphones and can give you those.
Any comments from either of you about Diablo Canyon in San Luis Obispo?
Diablo Canyon has a safety committee that reports straight to the governor. I talked to the guy who was chairman of that committee. He says that They have higher, Diablo Canyon's up on a cliff, they don't have to worry about tsunamis. Their design basis earthquake is, he says, quite conservative for this area. The San Onofre reactor has a higher seawall than Fukushima does. Its emergency generators are up on a cliff while the reactor itself is low. But all these things are going to be reviewed. And I think that for our reactors in California, the biggest question is how long do they have to stand on their own?
All right, how about right back there?
Can I toss in a comment there?
Oh, sure.
The American reactors almost all have big diesel tanks that are underground. Not so much because of fear of tsunami, but because of hurricane surge or cyclone things. And tornado, excuse me, not cyclone. Most of them have a day tank which run the diesel generators for many hours. The possible change to be made after Fukushima is that they will have yet a larger requirement for diesel, which could be used to run diesel fuel, which could run the diesel generators, could also be running emergency pumps, could be running fire trucks. Some of these places have bought fire trucks to move water around. And they're also likely to go from having either 8 hours or in most cases 4 hours of batteries. You could the 72 hours. Those would not be very expensive. They are the kind of thing that the NRC is looking at now. After the Hurricane Andrew in Florida, the Florida Power and Light reactors, Turkey Point, went for many, many days sufficiently on their own. Shut down. Of course, there was no grid to connect to it. But they came through with superficial damage and no longer lasting damage. And as at Fukushima, devastated, but the reactor was still standing.
Okay, I was wondering if either of you have any estimates for cost increases or time to build increases that could result from regulations that will stem from the
You faded out at the end there.
cost increases or time increases from. Oh, it's. Yeah, turn the microphone on. Is that okay? It's a lot better. Do either of you have any estimates for cost increases or time increases for building nuclear power plants that might result from the new regulations, new safety regulations stemming from the accident in Japan?
I don't think it's possible to say anything about that now because the NRC review hasn't been done. What are they going to do? I think at the minimum they're going to require that plants live on their own for a longer time than they do now. The impact on cost of just that is small. The other stuff, we just have to wait and see. Can't tell you. I can say one thing about prices, by the way, that the cost estimates for one of these new plants in the United States is quite a bit higher than the cost estimate, the actual costs for similar plants that have been recently built in Korea and Japan. And one of the reasons for that high cost is that there hasn't been a reactor built in the United States in a very long time. So our infrastructure for building reactors has decayed away. It's going to have to be built up, and that's reflected in the cost estimates for the first round of new nuclear reactors. You got to get past that, and I think Matt is quite right. The big competition now is gas. Gas is so cheap, people are going to go that way first.
I would agree with all of that, but I'd like to add that some of the new designs are intended to allow provision of water, cooling water, without very little electricity. The schematic that Bert tries water reactor is an AP1000. It has about the same amount of water in reserve anyplace else, but it keeps a roof. Gravity will still operate no matter what else happens. It has vastly few safety groups and valves because it doesn't need them. It's also set to passively give off heat, so it can't in theory, get as hot
Thank you. Okay, all right, thanks. Okay, how about, let's go back up further. Yeah,
I'm not a Stanford student, by the way, so is it okay if I ask a question? The question is actually in 2 parts. Would the advent of high-temperature gas-cooled reactors change the technical and commercial equation on the high end, and thermoelectric generators, such as are used in our spacecraft, on the low end?
I'd love to take a crack at that.
Yeah, go ahead.
The advantage of a high-temperature gas-cooled reactor is traditional light water reactors make electricity. Electricity is cheap. A high-temperature gas-cooled reactor could be in business not so much to make electricity as to split molecules. And when you do that, you're substituting for heat. You end up with hydrogen you could run through a fuel cell in a mobile application like a bus or a car. You end up with hydrogen that you can add to fossil fuel reserves, heavy oils, and turn them into gasoline fairly cheaply. But I wouldn't say at this point we have the advent of high-temperature gas-cooled reactors. What we have is plans. The best reactor is the one you've never built because you don't know what its complications are. These things never get easier when you actually start bending metal and constructing. They only get harder. So, as projected, the high-temperature gas-cooled reactors look lovely. The pebble bed is built one, ran it a few years, keep on it. The South Africans seem to love it, defunded it. It now looks like the Chinese may actually build one. The Chinese have money to throw around. But when you get up close and you get into the details, some of these things don't look as good in a hypothetical sense.
I'd like to give a little different answer to that question because after much prodding, the DOE is finally doing a very sensible thing. I call it analysis in multiple dimensions. If you're talking about the next generation of nuclear reactors, you should be considering the cost to build, the cost to operate, the cost of electricity, safety, sustainability, spent fuel treatment, and proliferation risk. In this multi-dimensional space, you have to analyze all of the alternatives. And it may be that when you consider them all, it's going to depend on how you balance them. I'll bet you the balance is going to shift more towards safety after Fukushima. But all of these other things, what to do with the spent fuel and proliferation risk, et cetera, are going to come into it too. And if you consider it that broadly, it's not clear which of, I'm going to call them Generation 4 reactor designs is the right way to go. This analysis just started, I think, about 6 months ago. It's got a way to run. When it's done, it's got to be put out for criticism, and then they'll come back, and I think that will give us a better idea of which Generation 4 technology to go with. There are also the small modular reactors, which are touted to have certain advantages over safety, initial capital costs, et cetera. I don't think it's so simple as to just say gas-cooled, high temperature looks like the way to go. How about this guy down here who's been struggling for...
Thank you so much, Dr. Richter.
He has the look of a student.
Thank you, Dr. Richter. You showed us that wind causes about 1/10 as many deaths as nuclear power, and in the United States it costs about 1/5 as much. It's competitive with coal. It has been competitive with coal since 2005 at 4 to 5 cents per kilowatt hour. And with pumped storage hydro, we know how to balance grid demand, so it doesn't matter when the wind's not blowing. We can use wind power from 1 to 5 in the morning to synthesize fuels for a $45.
I love that question. I love
per
that
barrel.
question
So the
because
question-
all the premises that you've given are just wrong. The only reason that wind power costs so little is because of massive subsidies. Now you have to, excuse me, my turn. Massive subsidies. You have to ask the question of what is the total cost. It may be the ratepayer paying part, but the taxpayer paying the rest. There's an analysis that's been going on in how much wind can you actually incorporate into the electricity mix now. In fact, the California Council on Science and Technology, looking at 2050, found that you could not do the goal of greenhouse gas reduction without putting in nuclear. A problem is we don't have the grid to transmit wind from where it is to where you'd like it to be. And the intermittency is a problem that has to be dealt with. And there is no universally available grid-scale storage gigawatt days, not megawatt hours. You can talk about pumped storage, it's good, but you gotta have a lake, and you gotta have water, and you don't have that all over the place. So I think I'm a fan of wind, believe me, but looking hard at wind, you might be able to do 10 or 15% of our electricity by 2020, and you should also know that Germany has just forbidden the addition of any more wind because they can't keep the grid stable with the anything more than they have now. So anyway.
Okay, I'd like to get back to the nuclear topic. This will be our last question, and up there in the audience, right? Yeah. This
Ask
is,
a tough one to Matt, please.
Hi, I am interested with most of the modern nuclear plants being built in the developing world. Do you think the regulatory and quality control measures in place are sufficient enough in those countries to prevent greater disasters of greater magnitude? Thank you.
I can give you a personal opinion. I think that is something to worry about. I think that one of the biggest problems is the regulators. And the International Atomic Energy Agency has a program aimed at training regulators for developing countries. It's a serious issue. I think that it's got to be further addressed, and it's worth worrying about. Matt?
I didn't quite hear the question. I heard some quality control. The problem in Fukushima wasn't quality control, it was design.
No, Matt, the question is about developing world countries getting into the nuclear business. Do they have regulating infrastructure? Is corruption a problem? Are they going to obey the rules? Is it more dangerous there?
Well, I was out in Pittsburgh, Pennsylvania a month ago talking to Westinghouse, which is fabricating parts now for AP1000s being built in China and hoping to sell them around the world. Supposed to get final design approval from the Nuclear Regulatory Commission later this year. Bert, you mentioned this before. When they export the components for the reactor, there's an intangible they're exporting there, and one NRC seal of approval. It is possible to take well-designed Western products, a Boeing 737, and fly it into the ground. You have good local operators. I think the airline is pretty good. If you look, for example, at the Middle East, is there that are flying European or American-built jets using European or American crews. It's like a pickup basketball team where nobody is local. If they're good, they will select competent people from the outside. They don't have the native experience, and they're never going to. There's an old Greenpeace accident anywhere is a nuclear accident. Every to best practices, look at each other's problems. The World Association of Nuclear Operators tries to do that. The IAEA tries to do that internationally, not quite successfully. One hopes that countries building these things without any infrastructure will rely heavily on other that are.
Okay, well, thank you. So this is certainly a topic that we're all going to keep thinking about and learning more about as the rest of this story unfolds. So I want to thank our speakers for giving us a really fantastic introduction to this.
For more, please visit us at stanford.edu.